be a part of this once again. And what we're going to look at today, and this goes out to all of the people joining us, is we're going to talk a little bit about what is important in networking, what the foundational information is, and we're going to make a little bit of an approach to looking at 4 different things relating to that. We're going to talk about the OSI model. Now, for anybody who's ever attended a data class, you know that as an instructor, we love the OSI model. And I very much think highly of the OSI model, even if we don't actually really use it or it is functional in any real sense. It is a way of looking at and determining how information should be exchanged. And to bring up another term, how information or communication should be exchanged is a protocol. We do that. And so the OSI model provides that framework of how the protocols operate. That's one reason why instructors are so fond of that. We'll also take a brief look at a couple of functionalities in that the networking components of a switch and what a switch does, and the networking component of a router. And again, a brief review of routing, and then a view of our favorite protocol, that would be TCP over IP. And if we look at that and think about it for just a moment, and the way I stated it, TCP is layered above IP. And so whether we like that OSI model or not, the layered model is a very strong approach when doing networking. In fact, the term TCP over IP represents that directly. And we'll take a brief look, and I do mean a very brief look, at subnetting, because of course, even now that IP version 6 has gained a much stronger use than it ever has, we still use IP version 4 in a number of different areas, and IP version 4, in order to be effective, must be managed through subnetting. So we'll take a brief look at the impact of that. And of course, the reasons to look at this would be, if you're going to work in networking, one assumes that you are going to provide design, and you can't design a network without this basic knowledge. You cannot operate and manage without these foundational levels of material. And of course, to be an effective troubleshooter, one must be able to understand the underlying content of these protocols. Now here we look at the OSI model, and what the goal of this is to identify the roles and responsibility at each level of communication, so that when communication is established, we know what's going on at each of these individual layers to create a manageable function of the exchange of this data. And it also gives us the ability, as people who talk about this, i.e. the instructors, to explain their components and functionality using a common framework. And so within this framework, we see that at the lower level, we're looking at mostly hardware. And the network at its layer 3 contains an IP address, and we know routers are responsible for sending IP address information. The data link layer is an exchange of source and destination MAC addresses, which are used on switches to effectively forward data from one system to another. And of course, the movement of that information flow is across a physical medium. Now, that physical medium could be a cable, and that one's easy enough to see, but we also know that it can be air, in which you are using wireless communications to send information from one system to another. Air is your medium of transmission, and that has physical consequences. The upper layers, mostly software functionality, can conform to the applications running on a system. So if we were to look at this in a slightly different way, we can see that there is a device on one side, we'll call that a client, and a device on the other side that's a server, and we will use our client server model to establish communications. And if we were to take this one step further, we note that the application would have one bit of information. And as we drop down here, you can see the slide expanding out to include the various information at each one of these headers to deliver that data across the link. And you can see it changes into the ones and zeros. It arrives at the physical interface, passes it up the track to the data link system, to the network, looking at that header, examining the transport header, a session header, a presentation header, until it arrives at the application header, and then it's sent to the application. So if we were looking at the delivery of, say, a picture from one side to the other, the picture would now be shown as it is on that particular screen. And the control over that distribution would have been handled at each one of those various layers. And I want to walk through that again to remind you that the client put on a application header, a presentation header, a session header, and so forth on these particular elements. The network header, the data link is going to go to the front of this, and that's just their conceit. They will flow as a big block of data link information, and you're looking for source and destination pairings in this. Did the device sending this at the network level send it to this device's network structure, and so forth? We want to make sure that it arrived. We want to make sure that it arrived intact and that everything was functional, so that when our application attempts to view the image or the content of that particular delivery, they have that information available. In this case, Chong, the SH, PH, and AH simply stand for the session header, the presentation header, and the application header. And I will say this, that those are made up. We will not see these in the actual TCP over IP model. But theoretically, if we were using the OSI model, we would see those things in that sense. Now, as I noted earlier, the physical layer is responsible for moving the bits from one system, one device to another device. I made mention that we can use wires, and the two common types of wiring are copper as well as fiber-based communications. Also, wireless allows us to establish communications at a physical level as well. If we move one step beyond that, we go to the data link layer. And the data link layer is the world of addresses. And if I had a home, this would be the address on my home. If you want to get something to me, you send it to my address, and then it would come in, and then I would look at the address and look at the top of that letter that you sent me. It's for Lane Williams. Why, that's me. And it could be sent to my wife, Heather, or my daughter, Sarah, or my daughter, Rebecca, or my daughter, Bailey, or my son, Trey, depending upon who the destination is. So we can break it out even a little bit more in that, but you got to get it to our house first. And that's the functionality of a MAC address. What is your address on the street in which you live is kind of one way of saying that. And the street is the network address. The MAC address is your home address. And we use both. That's why you always see a comparison in this communication between mail delivery, because it's something we use every day in the appropriate functionality of these deliveries. Now, at the network layer, this exists so that we don't all have to be a member of the same network. That would be enormously complex. There's a whole lot of traffic that you use to talk with your neighbors, and that traffic is okay because it's bound within an internal network. And this also allows for security functionality, but in the big world, the internet, we want to be able to move from one network space to another network space. We want to get off of our street and move on to someone else's street, if you will, or get out of our city and go to somebody else's city. And that's through the use of these IP addresses. They give us the big picture. If a MAC address is known as a physical address, then an IP address is a logical address. And one way of seeing this is if I take my laptop, and it's the same laptop that I use in-house. If I take that laptop to Starbucks or McDonald's or some other place offering wireless, I am going to use the same MAC address, but I will get a different IP address because I am now within a different network. And I need to have the appropriate addressing to send and receive information with that address that is found within that network. And so the peers within my network will discover what my MAC address is and allow me to communicate outside of that particular network. Or if you will, you think about it a little bit like location, then that's a good idea for seeing this. And that also brings us into the routing functionality. Routing exists because not everything can be found in my network, and I may wish to go to other networks, and routers provide that ability to move from one network location to another. If we think about this like you might a telephone call, a big telephone switch somewhere out there, or the SS7 signaling database would look up a phone number and then send it to that other side, allowing us to talk outside of our own local location to a remote location. And routing is how we discover where that remote location is found. With the telephone company, they look it up in a database. With IP-based routing, we have great big routers in the internet that handle that functionality and responsibility of collecting the locations where these networks are found and sharing that information with other routers so that we can get to our preferred endpoints. Also, there is a level of prioritization. This has not always been true, or it's not always been used in the internet or in networking in general, because we did not need it. But with the arrival of voice over IP, and that's another reason, if you wanted to do voice over IP, you need to know these network foundations now, that you need to prioritize that particular flow because, well, in all cases, a voice call is remarkably different from a data flow in so many different ways that it required that we change the prioritization, that we provide priority for voice transactions where data did not actually need it. Now, to kind of bring this up one more layer, we see that the transport layer, which we're now concerned with software, is responsible for a couple of different things. And arguably, this is the most complex of the communications because the responsibility of this is to make sure that the data that I send out of the interface is the correct size. And there are a number of factors that can determine what the correct packet size would be. And if I'm sending out a large file, and when it says large packet, it really should mean read large file in this case, I have to chop it up into smaller segments. Those segments would contain a specific byte count that my system had negotiated with other devices in the network to send out that data. In addition to that, this layer is responsible for error handling. If I send a packet and the other side doesn't receive it, there is a built-in mechanism for the recipient to say, hey, I didn't get it. Can you resend it? Now, that is true specifically for TCP over IP. There's another protocol, UDP, that doesn't follow that rule. But for the most part, we're going to talk about the transmission control protocol that's part of the transport system in this. The other functionality of this is to allow one service, the client side of the service, to talk to the server side of this service. And we make use of a function known as a port value for that. So when my client talks to a web server, it attempts to open up a communication channel to port 80. Or if it's HTTPS, to port 443. If it's email, it's port 25, port 110, or port 143, depending on whether it's SMTP, POP, or IMAP, all protocols of that type. If we're using file transfer, that makes use of port 21. And by the way, the client needs a port also, but they're going to tell that server what port that they're using. And the server knows who's talking to them by the use of looking at the source IP address, one of the things found in the IP header that says, when you send it back to this source, as well as in the TCP header, there is a source port value, and that server would send it back to that source port. So that's how the server knows how to communicate back to the client. When that is in place, it's known as a TCP session. And I lost my mouse. There we go. Now, there is a device in the network known as a switch, and a switch is also kind of complicated. At first, these devices within the networks were not complicated. They were known as hubs, and a hub would take an incoming packet and forward it out of all available outgoing ports. It was simple enough, but it was not intelligent. And arguably, the difference with this is that a switch is indeed an intelligent element. And the intelligence of this is that it understands, I should have gone through a little thing that ran added some more information to this table. Oh, it's on the next one. That was my problem. I do apologize for that. This is the one I wanted to see. And here we see that the devices, device A, B, C, and D, have MAC addresses, and they're built into the network interface card on that device. And the job of a switch is when you plug that cable in and the link comes up, to watch the source MAC address that's in the Ethernet header arrive at the interface and place an entry in the switch's lookup table so that you now know where a target system is. So when device A sends a frame to another device, its MAC address is updated in the switch's lookup table. So what they're saying right there is that device A, physically connected to port 2, is now going to be located in port 2, and the switch knows that. If the switch learned a little bit more about the destination, and in this case, the destination was device C, then we look in the lookup table that says that the device C with the MAC address of 00104C is the device that we wish to talk to. And they didn't show that clearly on that slide, but that was what they were looking for in this, using that lookup table. And as they continue on, when C sends a reply, which is what we're seeing right now, the switch adds C's MAC address to its table, forwards the frame, and sending it only out of port 2. What this means in a number of different ways is that B and D, those two devices could be talking to each other simultaneously to A and C, and then the past networks that simply was not allowed. It also indicates that we have moved from speeds at initially 10 megabits per second, which is 10 million bits per second. That's a lot of data flowing between the devices, to interfaces that now move at 100 megabits per second, a gigabit per second, 10 gigabits per second, and 40 gigabits per second. And we're on the edge of 100 gigabit per second resources. And a gigabit is a billion bits per second, and 100 billion bits per second flowing out of that. On switches, simply not a problem any longer. So there's that frame. It comes into the device. The Ethernet frame or the Ethernet header looks like this. The destination address is the leading 48 bits, and we see that value equal to the switch lookup table's value of 2. So it's sent to 2, and away we go. And the traffic would leave only that interface and arrive at that device. So that's a quick overview of what switching is doing, but it really doesn't do justice to the power that brought forth the idea of switches. Now, this page I only want to spend a moment on because the complexity of the protocol is very important, and we no longer really use this particular protocol anymore to protect the network. And in order to understand the functionality of the spanning tree protocol, what we have to understand is that there was a predecessor to a switch, and that device was known as a bridge. And bridges had a couple of problems. They generally had very few interfaces and not enough memory to do their job. They functioned a lot like a switch, but without a couple of other things. And bridges were popular about the time this protocol came into play, which, by the way, is the year 1988 in which this protocol was established. And it was created to protect bridges that would physically be connected in a loop. And so what you see here is the physical connection of these 3 bridges. And from a standpoint of networking, these devices, while they may be switches, are known as bridges for the protection in the spanning tree protocol. So it's much more likely that we call this the root bridge, the device we see over here, rather than a root switch. Even if we're talking about switches, we still call it that. And what the spanning tree protocol does very simply is this. It determines who the root bridge is through an election process. And again, we'll not go through that, but it is an election. We then, if we're not the winner of the election or we did not become the root, then our next responsibility is to determine what our best way to get back to the root is. So this root bridge would have 2 forwarding ports, this one right here and this one right here. And these ports would be their bridge ports. They're connected to the bridge. And so that's how they get to that location. Then, now that we know that communication can be shared against all of the different interfaces in this, we're going to block the link that is between these 2 devices. And most accurately, we're going to block this port. This device will send data, but this device will not receive any of the data. And by the way, if you have a spanning tree problem or you did not set this up correctly and your spanning tree did not work, then you can bring the entire network down with this looping functionality. So spanning tree, as well as rapid spanning tree, shortest path bridging, another protocol that I can't think of right now, all of those provide the functionality of creating a loop-free topology, which is the goal of these devices. So spanning tree would do that for that system. Now, here is our routing overview. And with the routing overview, I want to just say a few words about this. And for that purpose, I'm going to write down a few additional things on this. And that is, there are 2 types of routing protocols, IGP and EGP. and the E was not supposed to be a lowercase. IGPs are interior gateway protocols, and these would be the protocols that you use on the inside of your own network, be it a small little network or a great big large network. You get to choose how you're going to make forwarding decisions. As an IGP, you might choose RIP, not likely, it's a rather old protocol. OSPF, a lot more likely if you want standards-based, or IEGRP, a Cisco proprietary protocol. And I got that backwards. It's EIGRP, Enhanced Interior Gateway Routing Protocol. So those are the three common protocols for your network, and some things that they share in common is that this LAN right here, we'll call that LAN A, wants to communicate on this network, so it shares its functionality, i.e. I'm LAN A, with its upstream router, and then that router will tell everyone else in this network that if you want to get to LAN A, send me that traffic. And these other devices will create routing tables that determine what the best way of sending that traffic is based upon the protocol choice, the distance, the speed of the link, and other communication parameters that make sense within that network. So you can pick and choose from these. And in fact, you don't even have to choose one. You can choose for various reasons, multiple interior gateway protocols. But if you want to move to the exterior gateway protocol, you really only get one choice, and that protocol is BGP, or Border Gateway Protocol. And this one is the protocol of the internet. And if I take your singular network and identify it as a one unique entity, that entity would be known as an autonomous system. It's autonomous because it belongs to you, and you get to make all the decisions in that particular space. So you make those decisions, and within that particular variant, you share the information into other autonomous systems. And the complexity of this is found within the BGP protocol. RIP is not very complex. OSPF, certainly more complex. EIGRP, more complex. BGP, the most complicated of all. But I sometimes wonder if it is because attempting to route for the internet is an extraordinarily large responsibility in any case. The routing decision process can go through a number of different characteristics. As long as there is at least one route, we will go out that route. If there are multiple routes in our routing table, we'll make the longest bit match first. Usually we won't see something like this because, well, your routing metrics will determine exactly which of these are entered into your routing table. And with RIP, it would take into account the hop count metric for OSPF bandwidth. And for EIGRP, you can determine what you're using for that, such as any arbitrary path costs that you make up. It's your network, you get to do what you like. You can also look at things like reliability or delays or load or utilization metrics for that. But commonly the bandwidth metric is the most efficient and effective. And here we see that carried out briefly on the next slide. What the best path would be dependent upon the protocol that you chose for this resource. And if you chose one of these, RIP, the best way to get from one router attached to LAN A to the router attached to LAN B would be that 10 megabit per second link. But that one has the smallest amount of bandwidth, whereas if you're focusing on bandwidth alone, you're likely to use the router that says it depends upon the routing protocol RIP, OSPF, EIGRP, and to answer the question is what is the best data path to get there. And at the end of the day, it is the decision of the administrator of the network. Then they can override any of these routing protocols by themselves. Now, I made a big pitch for the idea of an OSI model, and then Chong called me out on it and said, what does this SH, PH, and AH stand for? And so I had to tell him, well, I was just making stuff up with that. But now I have the opportunity to not make up anything. And this is exactly what TCP over IP looks like. And this is the layered approach that we see in this model. You'll see it is a 4-layer approach rather than the 7-layer OSI. And it consists of these 4 layers, a network access layer. And there is at that header, at that layer, a header. Commonly, it's the Ethernet header, but if we're on Wi-Fi, it would be the Wi-Fi header. If we're on other protocols, such as the point-to-point protocol, we would see that header in there. But most commonly, it is Ethernet. And sitting on top of the Ethernet is the IP protocol. You see that and its various responsibilities. We recognize EIGRP and OSPF as routing protocols, and they sit within the IP version 4 function so that they may share the routing information. ICMP is network diagnostics for IP, and you'll note that it sits right there within the IP header. All of these point to a number. You can see an 88, a 1, an 89, a 6, and a 17. And this merely tells you what comes next after the IP header. So, or am I going to look at EIGRP information because that number is 88? Is it 6? And so I send it to the TCP process. Is it ICMP? And I send it to the ICMP process. This allows me to manage and look at those types of resources. The port numbers are found at the transport layer. And as you note that there are 2 types of transport, TCP and UDP. And depending upon the protocol and the functionality of the protocol and other resources, we see them choosing TCP commonly for some of our most common protocols, Telnet, FTP, email or SMTP, HTTP, as well as HTTPS and DNS. Now, DNS has 2 responsibilities. That's why you see it listing on 53. If you do a DNS query, that's where you say, I want to know what the IP address of www.google.com is. That's going to make use of UDP 53. If you want to take the content of your DNS server and back it up to a secondary DNS, that will use TCP port 53. So it's the same service, but a different functionality within the service depending upon the port in use. And you can see a couple of the ports used within UDP, and I'm not going to go into any depth on those or anything else other than to state that they are there. These are the server ports. The client will make up its own port number when it is communicating. Our next slide, it takes us into the world of IP addressing. And with IP addressing, we need to make note of one thing first, and that is that the IP address will attempt to tell us 2 things about this communication. The first is what network are you a member of? And that's used by the routers to forward you to the correct network. So if this were broken up as it is, 172.16 would define the network, and the host within that network is 200.1. Now, a couple of things about this. There can be no other device that exists in the entirety of the internet in terms of a public address that can be 172.16.200.1. We can have another device, say 173.16.200.1, because it's not in the same network. The host 200.1 is not in the same location. Likewise, we could have a 172.16.200.2 because that is a different address in and of itself. But some part of the leftmost bits moving towards the right define the network. Some bits from the right moving towards the left define the host. And we can set that at any bit setting now. It used to only fall on those points where we had the periods or the dots separating those values. You could have a network that was essentially just the first bit. Let's use a little pointer at that. If you only use the first bit, that was a class A network. If you used bytes 1 and bytes 2, then that's a class B network. If you use the bytes, first byte, second byte, and third byte, that would create a class C network. Now we have decided that a better way of doing that is to handle this more discreetly or more accurately by going back to our roots. And the roots of this are machines see an IP address as that top image that you see right here. I as a machine would look at the IP address and go, it's 1100000010100010100011001000. Okay. Well, we also want people, or at least the idea was originally that people might want to be able to memorize their own IP address like you would a telephone number. So based upon that functionality, we decided that we're going to take these 32 bits and breaking them up into equal values of 8, and that would give us 4 equal values of 8, and call that breakup an octet. It is a byte because it's 8 bits, but in networking terminology, we're much more likely to refer to it as an octet. And then we're going to translate that individual octet to its decimal equivalent. And so if you can count in binary, and I urge you to begin learning that if you really want to do networking, because I want to remind you that the machine sees it as that string of 1s and 0s. And you should be able to move from 192 back to 11 followed by 6 zeros. And briefly, what that's telling us is I have a value of 1 in the 128 field. That one's this leftmost field. The field next to it has a value of 64. The field next to that is half that with a value of 32, 16, 8, 4, 2, and 1. And if those bits are turned on, then we see that value. In this case, 128 plus 64 plus 0 plus 0 plus 0 and so forth yields 192. 101010 is the 128 and the 32 turned on, so that's 160, and then that next one is an 8 value, and so we see 168. 10 represented in binary is the number that you see above that, and the 100 is just below that. So when we as people talk about this address, we call it 192.168.10.100. But as I noted before, and the next slide will clarify this a little bit further, that I can take and separate these out, not just simply at the breaks as we did before, class A, class B, class C, but at any place I want along that string. So I can use any of those subnets that make sense to me. The prior bits would determine the network. The lower order bits would determine two things: the host space as well as the total number of devices that fit into the host space. Now, briefly, if I have a net mask that stops right here, that level right there, and there are only 3 bits left for the host space, I can only create 8 permutations within those 3 bits. And I'll give you a quick breakdown of that, of the 8 different permutations that it can exist in. It can be 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1. We'll come up here and do it in a down from this and set that first bit to 1, 0, 0. We'll do this one at 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. So that's all of the addresses that I can give to the hosts, or those 8 addresses. And that's not quite true either. It turns out that I cannot ever assign a host a value of 0, 0, 0 or 1, 1, 1. Those 2 addresses are reserved. The all zeros indicates the network and is used on the router for routing purposes, not so much for host purposes. The 111 is known as a broadcast address, and that allows me to talk to all members of this subnet in a single packet, meaning that the destination address of 111 in the host field must be listened to by all devices that are members of that network. So this creates the ability for me to now right size the network by adding in that additional functionality of a subnet. And that's what our next slide tells us, that we have what was initially the network and the host space, and we can add in a third tier. But the problem is that I only really have 2 types of bits in an IP address. They're either network bits or host bits. And so what subnet bits are this. They were bits that were found inside a network. So they were originally host bits. And these host bits have been given to the network. So now the network goes out to that particular location. So if I were to break this out very quickly, the functionality of a network with a 255.255.255.0 would yield one network of 256 addresses. And as we talked about on the prior page, that would be 254 hosts. And I'm going to use the host. So remember, I subtracted 2 from that. If I decide to subnet that network, then my net mask would look like this. That's 255.255.255.128. And that would allow me to create 2 networks. That's what the subnet is doing, is giving me the ability to add more networks, but I now only get 126 hosts. Now, once again, the total number would be 256 minus 2. yielding 254 because all zeros in the host field are all ones, and the host field belong to the broadcast and network, not respectively, or aside from that. So with two networks, we now have two all zeros and two broadcasts for those spaces. So the number would be 128 or 126 hosts. Now, the problem with net masks is the fact that I don't get to size it in just any way. I must use a bit count, and the equivalent bit count for this top one is a /24. The equivalent bit count for the one just below it would be a /25. So if we're looking at this, then we know that the next one has to be a /26. Well, now I have to ask myself, what do I get with a /26? Well, I'm going to get a net mask of 255, 255, 255.192. And if that sounds familiar, that's not surprising because it takes the next two bits in order and adds them together to get this net mask. And what I get as a result of this is 4 networks with 62 hosts. And I'll go ahead and continue this one by making note that that's 64 addresses. Now, what I had hoped to do with this is to give you just a taste of the complexity of subnetting, but it also should give you one other thing, and that is I had a network, or I have a network, and I have no more than 50 devices in the network. And I know that, and it's fixed at that level, and it's not going to change. If I use the older way of network addressing, I would have to take 256 addresses and assign them to that network. Whether or not I was going to use them, those can only exist in that network. With subnetting, I can take that same 256 address space and break it into 4 separate networks. I'm still wasting 12 addresses, the 62 between the 50, but I'm at least now much better off because I'm only wasting 12 addresses rather than 212 addresses or 216 addresses with that. And that's why we see these things. Now, you'll note that the questions to ask: how many broadcast domains? That's the 4 networks. How many IP addresses? 62 hosts within that. What is the range of addresses? Well, that one was a little more tricky, but I can show you that for the first network, the range of addresses is going to be really rather simple. And that was not my intention to move to the next page. So I'm going to go back a page and answer that question of what are the range of addresses. Well, it's like I said, it's kind of easy because if we can count by 64, then the first network would have the hosts of 0 through 63 decimally. The second network would be 64 through 127. The third network would be 128 through 191. And the final network would be 192 through 256. And here I'm using the full address space, not the subtraction that we saw for the other characteristics. So when we look at something like this, we see those types of things. Now, let me move that a minute and just simply show you that with all of this, we can make these decisions within our network. We can look at all of this data and determine what is appropriate for our network based upon the needs of our network resources. That's why we would do subnetting. It also consists of running out of different resources. The ability to translate between binary and decimal is very important. The octet boundaries, subnet masks, a number of things become important in this. And I hope to give you just a taste of that. And I also hope to give you a few, if you will, bad jokes before I take any of your questions. What does a network engineer do when he's lost in the woods? He's going to bury some fiber and then wait for a backhoe to show up. And that's very, very true. If you have something in the ground, somebody's going to dig it up at some point in time. Now, the next one doesn't yield itself very well to someone saying it out loud, because there are 1-0 types of people in the world, those that understand binary and those that do not. That is equivalent to 1-0 is 2 in binary. So why does HTTP stand for Hypertext Transfer Protocol? Because it had too much coffee, Java. Okay, that's not true. And these were known as Groner jokes. So